So, minus the square root of negative 284. I was saying we're basically ready to find x1 too. So this negative the square root of 284.92 plus 282 plus 0.47 equal to so negative 8.44 plus minus 1 over 2 times square root of negative 2.45. Here it comes. So this is basically negative 8.44 plus minus 1 over 2 times square root of 2.45 times the square root of negative 1. We're basically writing it in order to get ready for the negative numbers. So basically negative 8.44 plus minus 1 over 2 times the square root of 2.45 I. X12 is negative 8.44 plus minus square root of 2.45 I over 2. So this actually gives me x1 as negative 8.44 plus the square root of 2.45 I over 2, and x2 is negative 8.44 minus the square root of 2.45 I over 2. And we have basically found x1 and x2, so in this case they are actually lambda 1 and lambda 2, and now we're gonna find lambda 3 and lambda 4. So x3 4 is they're gonna be given by O over 4.4 times 1 plus 8.44 plus minus 1 over 2 times square root of negative 4 times 8.44 squared minus 2 times negative 141 minus 4 over 8.44. There we go. So this is actually minus 0 plus 8.44 plus minus 1 over 2 times square root of negative 284.92 plus 282 minus 0.47. Everything I just gave this the square root. So this actually becomes 8.44 plus minus 1 over 2 times square root of 3.39, which actually gives me 8.44 plus minus 1 over 2 times the square root of 3.39 times the square root of negative 1. We're getting ready for the the imaginary number again. This is actually 8.44 plus minus 1 over 2 times square root of 3.39 I. There we go. So x34 x34 is actually going to be given by 8.44 plus minus square root of 3.39 I over 2, which means that x3 is actually gonna be 8.44 plus square root of 3.39 I everything over 2, and x4 is actually 8.44 minus square root of 3.39 I everything over 2. So we have now found our x12 and our x34. So a quick recap: if we write, we get lambda 1 as our first eigenvalue as 8.44 plus the square root of 2.45 I everything over 2, which is pretty much roughly 8.44 plus 0.78 I. Lambda 2 is actually negative 8.44 minus the square root of 2.45 I everything over 2, which is roughly negative 8.44 minus 0.78i, so those two are the same. Lambda 3, we have 8.44. Oh, well, no, they're not the same. They're the same, but with the opposite sign. Lambda 3 is 8.44 plus, actually, the square root of 3.39i, everything over 2. So this is pretty much 8.44 plus 0.92i, and lambda 4, last but not least, is 8.45 minus square root of 3.39i, everything over 2, which is pretty much 8.44 minus 0.92i. So with this in mind, if we go back to not to this and not to this, but to where we started, so to our graph, we can actually see that indeed those are actually going to be within the circle. So let me just graph down. So lambda 1 is negative 0.44, so negative 0.44, so pretty much here, plus 0.78i, so it's pretty much here. So this is going to be lambda 1. Lambda 2 is going to be the same, but with negative I, so it's going to be negative 8.44, so negative 8.44. Actually 8.44, so it's actually here, right? So this is lambda 1 and this is lambda 2, so negative 8.44 and then plus 0.78i and minus 0.78i, and then we have lambda 2, which is negative 8.44 minus 0.78, so those are the two lambda. And we have lambda 3, which is negative, which is 8.44, so here 8.44 plus 0.92i, so 8.92i is roughly here, so this is lambda 3, and the same 8.44, so there, minus 0.92i, so here is lambda 4. And indeed, the eigenvalues are in the complex plane are within those circles. But the reason why I speed it up during this whole process, it wasn't just because it would have been taking forever for me to do that, and it already took me 1 hour, to be fair, to do this in the video, but it was to show you how the Gerschgorin circle work and why they are so important. Remember, at the very beginning of the part 1 of the video, we basically said that the Gerschgorin circles are given by the element in the center, with the element given by the value of the main diagonal, and the radius is going to be given by the sum of the absolute value of the elements outside, but in the same row. And this quickly gave us a graph with those circles in which we are sure they're gonna be the eigenvalues. So this is actually pretty impressive, because we just in a matter of minutes, like 1 minute or so, we can immediately see where the eigenvalues are gonna be. While if we didn't have the Gerschgorin circles, we would have been, doing this whole thing before even having a rough idea of where the eigenvalue would have been, which is far from simple. You have to take the you have to do many things. You have to find the characteristical polynomial of the matrix, which is a 4x4 matrix, so you have to use Laplace and then star rows, and then once you find the characteristical polynomial, you have to use the general equation for the quartic, which is far from being memorizable and easy. And once you compute all this, and it takes a lot, really a lot of time, you finally find all the values which are here. But you know, this is far from being straightforward. While with the 2 by 2 matrix is still doable, with the 3 by 3 matrix we are already in trouble, because we need the Cardano's formula in order to solve this. And with the 4 by 4 matrix we have the Quartic formula, but it's taking forever. And with the 5 by 5 matrix we have no formula, because there is no formula to find the values of a fifth degree polynomial. So what do? Well, we use the Gerschgorin circles. And this whole video is about not just telling you how the Gerschgorin circle works, but you know, it's about telling you why they are so important, and why it's important to know what they are and how they work. They're very simple, and they let you know where the eigenvalues are gonna be in a matter of minutes, like 1 minute or so. So they're very, very, very important. So this is pretty much it. I did all of this because I really wanted to show you, and because it took me forever to demonstrate this. But I wanted to demonstrate this because, you know, many videos just, you know, tell you what the Gerschgorin circles are, and then that's it. Like, all right, you can compute them and find them, and that's pretty much it. But you know, I do think that it's really, really important to know why they're used and why they're so important. Because, you know, this is the alternative, a quartic equation. You know, it's not, and a 4 by 4 determinant with Laplace and Sarus, and then 4 Sarus matrices, sub-matrices. So, you know, it's not very, it's not actually very, very good. And by the way, in a 3 by 3 equation is even worse, because with the Cardano's formula, even though if you're in the complex plane, you expect imaginary values, but even if you're not in a complex plane, for instance, and you have a 3 by 3 matrix, and all the values are going to be, the eigenvalues are going to be real, you may get imaginary numbers in the, you know, in the intermediate passages, like in while you're computing this, and while you're getting, you know, while you're doing this step by step, you might get imaginary numbers and then cancel them out in between. And then in order to get that, you with the Cardano's formula, you basically get only one root. In order to find the other two, you need to bring everything into polar coordinates. So it's madness. It's madness. It can be doable. I showed you the Quartic equation, for instance. And I've done also a 3 by 3 matrix with the Cardano's formula, but you know, it's madness. You shouldn't be doing this, and this is why Gerschgorin circles are very, very important.